Okay, welcome back. Now the problem I'm going to do, it's called the coil with a current wrapped around the sphere on an incline. The incline has an angle theta. So we have a sphere here, radius 30 centimeters, mass 2 kilograms. We have a magnetic field pointing down, 1.25 Teslas. And then there's a coil here wrapped on the equator. It has 50 turns. And the question is, the first question we can ask, what should the direction and magnitude of the current be in that coil? The direction and magnitude of current, so the sphere won't move. What is the required direction and magnitude of current in the coil so that the sphere remains stationary, remains at rest? Okay. Second part of that question, we can ask, what if we reverse the current? What if we reverse the current? What if we reverse the current? What is the initial acceleration? What is the initial acceleration of the ball as it starts falling down? What if we reverse current? What is I initial? The initial, what is the acceleration initial? Okay, so let's calculate this now. So what's going to happen if let's look at the forces and torques on the ball. Okay, so we have here mg. So this is a little bit of review of physics 1 material, and then we have here the friction force up, Fs, right? So the mg is pointing at the center of the sphere, so it applies no torque. The only force applying a torque is the friction force. So if R crossed into Fs, that's out of the board. So the torque due to the friction force is going to be out of the board, and it's going to cause the sphere to want to rotate counterclockwise. So usually out of the board torques cause an object to rotate counterclockwise like this, right? So the thing will start wanting to roll down the hill, of course, right? So if we want this thing to remain stationary, the current in the wire should be such that the torque due to the magnetic field should be into the board, right? So what is the torque due to a magnetic field on a current carrying wire or current carrying coil is equal to mu crossed into B. The magnetic moment crossed into the magnetic field, right? So how do we define the magnetic moment of a vector, right? If the current is flowing this way, right? So let's say on our side, the current is flowing this way, and on the back side, the current is flowing this way, right? So that means the magnetic moment is this direction. The magnetic moment is that direction, right? So the definition of magnetic moment is equal to I times the A vector. The current in the wire times the surface area of that. So if the current was flowing this way, the magnetic moment would be that way. Which direction would the torque be? So do mu crossed into B. So mu crossed into B, the B is pointing downward. The torque would be out of the board. Well, the torque due to the friction is also already out of the board, right? So we want the opposite to happen. So we want the current to flow this way, and then this way. So if you look at it from the top, we want it to flow clockwise. We want the current to flow this way, clockwise. Okay, so we want the current to go like this. And then in the back, we want it to go this way, right? So it's going to go like this. So then the magnetic moment is going to be facing down, right? Like that. So we can say the magnetic moment go like this. It's facing this way, right? Mu. Okay? So now if you do mu crossed into B, mu, and then this is B, mu crossed into B, into the board. There you have it, okay? That into the board torque, if it's equal to the out of the board torque due to the friction force, then the thing won't move, okay? So we concluded our first thing is that the current should be flowing clockwise as viewed from the top. So its direction is clockwise. Okay, so current should flow clockwise as viewed from top. Okay, so then the torque due to the magnetic field will be what? Mu, which is this one, crossed into the magnetic field B, so the magnitude of mu, the magnitude of B, and times the sine of the angle between them, this angle, right? Well, if this is theta, what's that angle? So we can draw the horizontal line here, the inclined plane, so this is theta, so this one will be 90 minus theta, and then this one will also be theta. So the torque will be, since it's the cross product of mu and B, it's going to be mu times B times sine of this angle. So it's just going to be mu B sine theta. Okay? So this is the torque due to the magnetic field. We want that to equal to the torque due to the friction. So what is the torque due to the friction? Okay? So the torque due to the friction is going to be R times Fs. R times Fs. So that's equal to the torque due to the friction, right? But then, how do we know what Fs is? Okay, so we have the normal force, then we can break the mg into components. This is going to be mg cosine theta, and then this one is going to be mg sine theta. Right? So if the thing is not accelerating, what's going to happen? N is going to equal mg cos theta, and then the friction Fs is going to equal mg sine theta. So then the torque due to the friction force, right, we can say is equal to R, and then the friction Fs equals mg sine theta. Mg sine theta. Okay? So then if this torque is equal to that torque, the sphere will remain stationary. So then we set this equal to mu b sine theta, and then theta, sine theta cancel. So then you have here Rmg. Then mu is equal to what? It's the current times the area. So since we wrapped it on the equator, the area is pi r squared, where r is the radius of the sphere, right? So it would be, mu would be the number of turns, Nia, right? Mu is Nia. Because we have more than one turn, each time the coil turns around once, you're adding more to the magnetic moment, right? So the magnetic moment is going to be N, I, and then the A is going to be pi r squared. Okay? So then we multiply that with the magnetic field B. So what are we solving for here? We are saying what should the value of the current be in order for this to be stationary. So we're solving for I. So one of these R's cancels this R. So then we say here I is equal to mg divided by N goes down to the bottom, pi goes down to the bottom, R goes down to the bottom, and B goes down to the bottom. Right? So the weight divided by the number of turns. So what does this mean? The more turns we have, the less current is required, right? If we have a lot of turns, less current is required. If the radius of the sphere is bigger, that means also that requires less current. Why? Because the bigger the radius, right, the more the magnetic moment is going to be due to the current, and then it's going to require less current. The stronger the magnetic field is, then we also require less current. But on the other hand, if the sphere is heavy, then that requires a lot of current. So you can see the equation makes sense. Now we put in all the numbers, which is 332.7 milliamps. So that's not a very strong current, very little current, right? Because we had so many turns, that really helped out. So even with a 330 milliamp current, the sphere will stay there, okay? Well then what's going to happen if we reverse the direction of the current? If we reverse it, then the current is going to be going this way, then the magnetic moment will be this way, and now the torque will be out of the board, so it's going to cause it to want to roll down also, okay? So then what happens here, okay? So then it's going to start accelerating. So now let's do all the forces and the torques on the sphere, right? So the forces is going to be what? You have here mg cos theta, then you have here mg sine theta, then the friction force Fs. So it's going to start accelerating down the incline, A center of mass. So it's going to be mg sine of theta minus the friction force Fs is equal to ma, right? So that's going to be the force on the sphere. How about the torques on the sphere? Well, the torques on the sphere, they're both going to cause it to roll down, right? So it's going to be the torque due to the friction force, RFS, plus the torque due to the magnetic moment. So what was the equation for the torque due to the magnetic moment? Right, the angular acceleration of the sphere. So then, what are we going to do now? We can express the area as pi r squared, right? Express the area as pi r squared. So n I pi r squared b sine theta, right? And then over here we have to express its moment of inertia. What is the moment of inertia? Well, now that depends, is it a hollow sphere or a solid sphere? If it's a solid, metallic conducting sphere, it would be different than a hollow sphere. So let's assume right now it would be a hollow sphere. And then the moment of inertia would be 2/3 mr squared. So 2/3 mr squared, so you put here 2/3 m r squared alpha. So then what happens? Well, one of the r's of this cancels with one of the r's here, then cancels with one of the r's here, right? So then you get here Fs plus Ni pi r b, Ni pi r b sine theta is equal to, then you get here 2/3 m. And then the next thing we do, this is always something we do from physics 1, we say R alpha is equal to A tangential of the edge of the sphere, and then A tangential of the edge of the sphere is equal to the A center of mass of the sphere, if it's rolling down with pure rolling motion, right? So this A will just be A tangential, and this is A center of mass, but then we're going to assume A tangential equals A center of mass, which just equals A. So then this is just going to be 2/3 m, then we replace that with A. Then the force equation, we can write it right over this, mg sine theta minus Fs is equal to ma, right? Then we add the two, okay? So then after that, we can just factor out the sine theta, and then that is our expression. So we have here mg plus n I pi r b, that times sine of theta, and then the 3 goes over there, 3 over 5m. That's going to be the initial acceleration of the object. That acceleration won't be constant, because as this thing starts rolling, the current will start shifting, and the mu will start shifting, and the angle between the mu and the b will change. So it's a complicated situation that's going to happen. It's going to start going like this, right? And then the angle will change as it starts rolling. So this only gives us the initial acceleration, okay? Squared. So the acceleration, the initial acceleration will be down the hill, right? And it will accelerate at 4.97 meters per second squared. Now, what if the question had said something else? What if instead of reversing the direction of the current, right, I had doubled the magnitude of the current but kept it the same direction, right? So let's say I kept it this direction, and remember the magnetic moment was this way, but instead of reversing its direction, I doubled the magnitude. So then what would happen? The current due to this would get stronger, this would get stronger, and it would start wanting to go up the hill, right? So then what would the difference be in my calculation? The torque due to the magnetic moment is going to win, and it's fighting against the torque due to the friction. So then this one becomes a minus, right? Then the thing is going to start accelerating up. So what's going to happen? The friction force is going to be larger than the mg sine theta. So this is going to be plus, this is going to be a minus. So the A centripetal is going to be up the hill. The friction is going to beat the weight. So then it's going to be Fs minus mg sine theta is ma. Then you have the torque due to the magnetic moment will beat the torque due to the friction, right? So does that change anything when you solve it? Well, you go through the same steps, and you can, after eliminating the r, right? So you have here a plus, and then you have here a minus, then you have here a minus and a plus, right? When you add them, you get pretty much an equation looking like this, right? But except that the mg sine theta is negative. So then at the end, you get an equation that resembles this one, but then this one is going to be negative, right? So you put here negative. So if we wanted to calculate the acceleration, I would put 3, then 5 times 2. This is going to be negative. Why? Because this one was negative and this one was positive, and then this one was negative. I add the two equations. This one it gets eliminated, and then you have here minus mg sine theta plus ni pi rb sine theta. That's equal to 5/3 ma, right? So then this is a negative. Negative 2, 9.8 plus 50. Then I'm going to put here double, 0.6654. Then I'm going to subtract the weight from that. So the value that I get should not be as large as 4.97. Okay? Where how magnetic moment gives you a torque, and it can either fight against or enhance the torque due to the friction, and they could either be in the same direction or in opposite directions, right? And then you can calculate the acceleration. So there's a lot of good physics here, and it's also a good review of some of the material you learned in Physics 1. Okay? Thank you very much.